Hi folks, I'm going to make this video and attempt to do the best job that I can to describe qualitatively how electromagnetic radiation is produced and why you end up with these wave properties. So I'd like to start this discussion with just a quick little reminder of what a dipole field looks like. So you have to imagine this is a positive charge, this is a negative charge. The electric field between them is relatively strong, points down. And if I draw some of the other field lines, they would look, kind of like this. This is not the best dipole field I've ever drawn, but the important thing to recognize is definitely the field between them is down, the electric field. And again, that's because the electric field is the direction that a small positive test charge feels a force. So pretend like you put a proton here, force would be down. Now, I'd also like to point out that if I go right in the middle and come off axis a little bit to like here, the electric field here points down because the electric field is tangent to the field lines at every given point. So this plus minus, again, that's referred to as an electric dipole, and it gives us an electric field configuration looks something like this. Again, similar to a magnetic dipole, which we just got done talking a lot about. Okay, so I want to keep this in mind for this example over here. So now imagine a wire or some sort of conductor, and imagine it's hooked to an AC voltage source, right? So a voltage source, remember, that's going back and forth, back and forth, back and forth. So what this voltage source is going to do is it's going to make the charge configuration on the wire vary back and forth between plus minus and plus minus, right? Because half the time the voltage is going to be this way, right, pushing positive charge up, leaving us with a minus and a plus, but half the time the voltage is going to be pushing charge this way, giving us a minus plus. So what it's going to be doing is basically it's going to be producing a dipole that's changing. Now we're going to talk about, all right, well, if we have a changing dipole, what are the effects of that? So imagine an instant in time where the bottom of this is positively charged and the top negatively charged. And then keep in mind that what we're going to have in this region here is a dipole field. If I go right off axis here, some point out here, the electric field would point up. Now, the voltage varies, so eventually what's going to happen is this is going to be negatively charged, this is going to be positively charged. So now what happens is the voltage flips direction. I'm sorry, the charge configuration flips direction and gives us a configuration that looks like this, plus minus. In this charge configuration, the electric field here points down. So you notice that the electric field is going to kind of reverse direction. And this is true at all points in space along this axis. This oscillating charge configuration is going to make this electric field go up, down, up, down, up, down. So what we're going to get is an electric field that's changing. So what that really means is we can represent those electric fields with a wave. And the wave is representing the disturbance in the electric fields. So what I'm drawing right now represents electric field vectors. So imagine this entire wave traveling to the right at a speed equal to c, 3 times 10 to the 8th meter per second. And then imagine a point in space. When this thing gets here, the electric field is down. When this gets here, the electric field is down but short. Then there's no electric field. Then it's up but short, and then bigger, and then smaller, and so forth. So as this wave moves to the right, the field here is oscillating back and forth. And it's not just the electric fields that are oscillating either. In order for this charge, this plus, to get down here, to take this from a plus minus to a plus minus, we need an electric current in this direction. Now, keep in mind that when we have an electric current, we also produce magnetic fields. So basically, superimposed on this, we have the electric fields that are varying vertically. But we also have magnetic fields that are varying in the other axis here. So this is not the best picture. This picture that I'm trying to draw here represents magnetic fields. So the magnetic fields, you got to picture a wave like this, where the magnetic fields are going like right, left, right, left, right, left. The electric fields are up, down, up, down, up, down. And you got to imagine this waveform, the entire thing propagating to the right. So there's my quick description of how or why electromagnetic radiation has wave properties, because it is a wave. And if you think about what is a wave, in general, a wave is a disturbance. So if you think about like a water wave, it's a disturbance in the surface of the water. Or a sound wave is a disturbance in the sound, or I'm sorry, is a disturbance in the air moving through space. Well, an electromagnetic wave is a disturbance in electric and magnetic fields that moves along with a speed c, 3 times 10 to the 8th meter per second. This thing's pretty tough to draw. Sorry about that. I'll try to get you some better pictures in the next video.